Welcome to the SFA Astronomy 105 lab. This is lab 11. It's the last lab before our final, which there will be a final. It'll be in D2L during your lab time. So normal lab time that you used to actually go to, make sure you go to D2L during those 2 hours. That's all you'll have to be able to work your test. All right, so please, please, please do not miss your test, your final exam. It is worth, I believe, 25% of your lab grade. It could be 20%. It's in your lab syllabus, so you can find out all that good information. Just please do not miss it, okay? And to prepare you, you should have, all the labs in order to look at them all. But in order to prepare you, you can take notes over this. I'm going to be going over some really important things in this PowerPoint. Of course, you have these PowerPoints available to you, and obviously you have this video, but study ahead of time. Don't cheat on your exam. It's not going to help you that much anyways. It's 50 questions, multiple choice. It's not that hard as long as you study ahead of time, alright? So let's get started. Here's our beautiful review. Oh, I forgot to change those, but it's during your normal lab time as your lab exam, and obviously you don't need either of those things because, well, we're doing it online. Make sure you have a good internet connection. Alright, so from every lab, including the one we're doing today, there were going to be 3 to 5 questions from each lab, and a lot of it will be conceptual questions. You're technically not allowed a calculator on the exam, so don't use one. What that means is that there's not going to be any really hard math questions. You do need to be able to recognize equations, what they meant, how you use them, what they stood for, what lab they were used in, but you don't need to actually perform calculations using a calculator, right? There is a little bit of math, but as long as you know, like, perfect squares, like the square root of 4 is 2, that type of thing, you should be just fine. A-okay. Alright. So, very first lab, sky familiarization, way back when we had our beautiful star charts. So hopefully you can identify some of this stuff. I'll start off this flat line. Give you a second to see if you can remember it. It's the celestial equator. The curvy line is the ecliptic. The ecliptic stands for the path the sun takes through our sky, so you can see that the sun is all along there. Now, when the sun is highest in our sky, and therefore highest on the star chart, right up here, you are in summertime. It's the summer solstice. So what months do you think are associated with that? Just, some helpful questions. On the flip side, the lowest point where the sun would be, way over, there, that would be the winter solstice. So what month is that associated with? Just sort of helps you get your bearings. Don't forget that you always move to the east. So you start here at the vernal equinox, that's at 0 hours, and you always move to where the numbers are getting larger. Alright? When you come over here and you run out of numbers, don't worry, you just go to the other side of the star chart. Bam, more numbers. Alright. So, some other things on here. We have our stars and constellations. The stars, star names are one capital letter, the rest are lowercase. Constellation names are all capital letters, like Betelgeuse and Orion here, as I just pointed out. The little dotted lines show you what the constellation is kind of supposed to look like, that type of thing. Alright, you do see some Greek letters, like gamma and beta and whatnot. Those are just other ways to name stars if they're not large enough to have actual proper names. Okay, these lines here along the celestial equator, they are called hours of right ascension. We measure it in time, like hours and minutes. So if you're exactly right here, it would be 6 hours and 0 minutes. Going up vertically, you can see that there are these other lines. These are your declination. If you go above the celestial equator, they are positive. If you go below the celestial equator, they are negative. All right. Don't think there's anything else I need to mention about this. Let's make sure. I don't know why I always forget that there's a lot of commands here. All right, now we want to find our right ascension. Oh yeah, a meridian. A meridian is any vertical line on your star chart, but in your sky, it is an imaginary line that cuts your sky in half going from north to south. All right, and the place that's right above your head is your zenith. So good words to remember. All right. How many hours of sky can we see at any one point in time? 12. How many total hours of sky are there? 24, just like a clock. You have 24 hours in the day, so you have 24 hours in the sky. And you can only see half of it. What are some things that affect what stars you can see in the sky? There is latitude for one, because if you're at the North Pole, you can't see any of the southern hemisphere stars. There is the seasonal stars, so if you're on the other side of the sun might be blocking some stars, and so you can't see those. And time of day, of course. You can only see stars at night unless you're wanting to observe the sun. Alright, so March 7th at 8 p.m. First thing we gotta find is what is closest to March 7th. Our star chart is set for 8 p.m., so that is good. We found March 7th. That is our meridian. We draw a line going all the way up and down. Now, it says 32 over here. What does that possibly mean? That's right, it's your latitude. You use your latitude to find where your zenith will be. So that is your zenith point on your meridian. If you waited too long to go out and it's 9 p.m. instead, then you would just move the line over 1 hour along with your east and west points. So, your east and west points, you start from your meridian and you count 6 hours over. That's your west point. It's just a little point on the celestial equator. It's not a whole big line. And we go this way. Well, we ran out of hours, so we have to go to the other side of the chart to find our eastern horizon. So that's everything that's visible. Everything that's not visible is where the sun is. You can see kind of where the sun is going to be. Now, be careful because the dates that are on the ecliptic tell you where the sun will be on those days. They are different than the dates at the bottom of your star chart that let you know where your meridian is. So don't confuse those. Right. I think I said most of that. Oh yeah, the meridian moves eastward 4 minutes each day. So if you do not happen to be on a perfect day on the bottom of your star chart, then you just add 4 minutes for every day that is passed. Alright. Scientific measurements. I like this lab, actually. So just remember that physical quantities can never be measured with absolute precision, because there's always some extra precision that your tools just can't measure. So we're going to be working with significant figures and scientific notation and how to multiply and divide those things. How many sig figs does this have? Well, there's a 0 here, so that's not a significant figure. And this 0 is also a placeholder 0, so it only has 2 significant figures. Next, we now have a 1 here that is significant. We have a 0 here. Now before it was a placeholder, but now, because there are significant figures behind it and in front of it, it's sandwiched in between, so now they are all significant. There are 4 sig figs. This one, you have a 1, a 2, those are both significant figures. And then you have 3 zeros. These are placeholder zeros, therefore they are not significant and you only have 2 sig figs. But what if I said that there were exactly 1200? That word exactly or precisely or any word indicating like that means that these zeros here are in fact significant, they just happen to be zeros. Therefore it would be 5, right? But you have to remember there's a difference there. You have to let the reader know when these are significant and just happen to be zeros. Alright, here These zeros are sandwiched in between, but they are all significant, so it's 5 sig figs. Beautiful. Here's scientific notation. I'm not going to go through that whole chart, but remember that you have to have, for proper scientific notation, you have one singular digit from 1 to 9, so there cannot be a 0 in this slot, a decimal place, and then the rest of your significant digits, right? So if you have any unsignificant digits, you drop them. If you have a really long calculator answer that has 8 decimal places, but only 2 of them are significant, because that's what you started with your calculation, then you drop the other 6 decimal places and you only keep those 2. All right? And times 10 to the whatever you happen to have there, so that's how many times you moved your decimal place. If you move your decimal place to the right, you make the number more negative. Your raised power becomes more negative. If you move your decimal place to the left, your raised number becomes more positive. So it's reverse from what you kind of want to think, right? Moving on to multiplication. We have a very easy way of multiplying and dividing our scientific notation, and this is why you don't need a calculator for these problems, especially on the test, right? They're going to be very easy problems you should be able to know, and I'm going to show you right now how to knock out your scientific notation without a calculator. So we have these two numbers here, they're both in scientific notation, they're both being multiplied, so we split them up. Split it up into the significant numbers, so 4.0 and 2.0, and your exponents. So now you say, what's 4 times 2? Well, that's pretty easy. It's 8, right? What is 4 plus 3? 7. Because when you multiply exponents, you just add them. All right, so 8.0 times 10 to the 7. Is that proper scientific notation? Yes. You have a digit, a decimal, the rest of your significant digits, and proper integer right up here to the power, all right? Let's try another one. 6.0 times 2.0. It's pretty easy. It's 12, right? 6 times 2 is 12. Then 2 plus 5. Easy. It's times 10 to the 7. Is this proper scientific notation? No, because you have 2 digits to your left of your decimal place and you only want 1 digit. So you have to move your decimal place over again, put it between your 1 and your 2, and that will change your exponent. Because you are moving it to the left, your exponent will get larger. It will get more positive by 1 because you moved the decimal place over 1. Alright, so now your answer is 1.2 times 10 to the 8. That is proper scientific notation. Notice that here you had 3 sig figs in total, 1, 2, 3, but here you have 1, 2, because you started with 2 sig figs. So you always want to end with how many you started. Alright, now if you are dividing, you do the same thing. You would say, what's 6 divided by 2? That would be 3. But then you subtract your exponents. So 2 minus 5, and that would give you negative 3. Alright, so same sort of deal, but subtraction instead of addition, division instead of multiplication. Units are incredibly important. We do a lot of dimensional analysis or unit conversion. So if you haven't noticed, you write your units a lot. You should always write your units, because if you don't, we don't know what you're talking about. There are a few examples of unitless numbers, but we can see that they become unitless as you do your work, for the most part. So make sure you know how to convert things. I'll do a little example here. We're trying to get 500 kilometers into centimeters. So if you just visualize it real quick, take a step back. A kilometer is much larger than a centimeter, right? So your number here, 500, because you're subdividing it, instead of being 500 kilometers, which is a pretty big unit, you're going to make it a much larger number of much smaller units, right? So your centimeters, very small, so you're going to have a lot more of them than 500. So it's just a quick little way to make sure that you're on the right track, you're checking your work. Alright, so here's our unit conversions. We put the kilometers on the bottom because we want them to cancel out when you multiply, and you want to be left with meters, then meters to centimeters, so you put the meters on the bottom here as well. So you'll have to use centimeters. Let's see how this math works. You multiply by anything on the top and divide by anything on the bottom. So 500 times 1,000 times 100 divided by 1 divided by 1. You cancel out your units. You are left with centimeters. You can plug that in a calculator, but you don't really need to because you're just adding a bunch of zeros to the 5, right? And we put it in scientific notation. Alright? None of those zeros were significant, so the only sig fig we had was 5. So we just say 5 times 10 to the 7 centimeters. Not too hard. Alright, the moon. Here we have Earth, moon, the sun, not to scale. And we are facing the Earth right now on the moon. You can tell here this is a new moon because from Earth you do not see any of the lit portion of the moon. Next, we're still facing the Earth here. From Earth, this moon is a first quarter because you can see a quarter of the moon is lit. Or really, you can see half of the lit side, and that lit side happens to be on the right, letting you know that it is waxing. Next we have our full moon, still facing the Earth. We can see the entire lit portion of the moon from the Earth. And last is third quarter. The left side is showing. That lets you know that it is a waning moon. So we show that this is synchronous rotation because the moon is always facing, the same side of the moon is always facing the Earth, right? So does the moon rotate on its axis? Yes, it does. It rotates at the same rate that it revolves around the Earth, and therefore it's called synchronous rotation. They're in sync, not the band. So what is the moon's hidden side? Well, it's not the dark side, right? Because here, on the new moon, we can see the dark side of the moon. That's what a new moon is, right? So the hidden side has to be that far side of the moon that we never get to see. It's always facing away from us. Right, so real quick, what phase is this? Well, I just said it earlier, right? It's first quarter. We can tell by that angle as well that it's first quarter. What is its rise time? We start on this side over here, and we're going to work our way counterclockwise. So the rise time for the moon is noon. What's its transit time? Sunset. What's its set time? Midnight. Don't forget these other words as well. So between sunrise and noon, we have morning, noon, afternoon, sunset, evening, midnight, night. All right? So don't forget about those words. Just review them a little bit. Mercury's orbit. We did a few things from Mercury's orbit. We talked about Kepler's laws in specific detail. We actually proved Kepler's laws, all three of them. All three laws of planetary motion. So the first law is that planets' orbits are ellipses. They look kind of like circles, but if you do the math, they are actually elliptical. All right? That's the first law. Boom, we're done. Second law, equal time in equal areas. Wait, equal areas and equal time. There we go. So you can see that this fat short triangle covers the same amount of time as this long skinny triangle. And if you find the area mathematically of those triangles, you will find that they are the same. They're equal to each other. Right? It's another little law. And if we move on to the third law, this is our harmonic law. So it is relating the semi-major axis. So here, the long part of your ellipse is your major axis. Semi means half, so half of your major axis. That is your A. If you cube your A, and it has to be an AU, astronomical units. Remember, for Mercury, it has to be less than 1 AU, because 1 AU is the average distance from the Earth to the Sun. So, since Mercury is closer to the Sun than Earth is, it does have to be smaller than 1 AU. But if you were looking at Mars, for instance, it would be larger than 1 AU. All right? And P, the period, so how long it takes this planet to go around the sun back to where it started in years. So P squared equals A cubed. And we use that law to help us find a cool thing. We weighed the sun. We found the mass of the sun. So here's how we did it. The procedures. Go ahead and make sure you read all the procedures for all your work and stuff. Like, it really does help if you read those intro pages that no one ever reads before they come to class. It really, really helps if you read those to prepare for your test. So, to verify Kepler's first law, we just looked at different points, and we remembered that they are all equal time intervals, right? Here's your major axis and your sun. You go from one focal point, which is your sun, to another focal point and back, and you measure the length of that line to 3 random points. And they should all equal the same length, and that length should equal your major axis. All right? The second law, you measured the same amount of time for each of these places around your orbit. Over here, it's much closer to the sun, right? So you see we went 3 in this example and 3 in this example. This triangle here is much longer and skinnier, but it has the same area as this triangle right here. You do the math. Look at your labs. It's good. Alright, and then we used this law, the harmonic law, to find the sun's mass, as I said before. You don't need to memorize your equations, but you do need to be able to recognize them. So in particular, make sure you can recognize what this equation is. Alright? Now, emission spectrum. I love this lab. I love all the spectras. Just a quick review of electromagnetic spectrum. If it has a longer wavelength, it has a lower energy, and it has a lower frequency. The higher the frequency, the higher the energy, the lower the wavelength. Alright? Now, there are all types of different light, and we can't see most of it. We can only see from 400 nanometers to 700 nanometers. Well, about. Everyone can see a little bit different. So some people can see a little past 700 nanometers. Some people can't even see that much. So it's a little bit of a give and take, but for the most part, you can roughly see 400 to 700 nanometers. Whew. And if you look at how long these can get really, really long. Like, these radio waves down here are larger than a football field. So it gets very long. There are 3 types of spectras. If you're just looking, remember Kirchhoff's law? He had 3 laws as well. If you're just looking at a source of light, then you see a continuous spectrum. If you look at that source of light, but there is a cool rarefied, which means the opposite of dense, it's thin gas, you will see absorption lines with a continuous background. Continuous backgrounds coming from the source, and the absorption lines are coming from the atmosphere in front of in our case, the atmosphere in front of the star. This gas in front of your source. And if you do not see the source, if you're looking at it but you only see that cloud of gas, you can see emission lines as long as that gas is still being excited. It has to get excited in some way in order to emit the light. Notice that because these are the same elements in the gas cloud, these lines match up perfectly. Every element has their own unique signature, almost, for their spectras, so that's how we can identify what elements are in different stars' atmospheres, what they're made of, what they're producing, all that fun stuff. There's some cool atoms. This isn't really how they look, but you can see that they like to jump in different energy shells, and that's what we kind of focus on for how spectrums work. Earth's orbital velocity. We introduced the Doppler effect. We love the Doppler effect. We use it all the time. So here you have a light source, or a source of some kind. I'm going to call it light. And it is just producing these wavelengths. Each circle represents a wavelength. The distance between one circle and the next is one wavelength, right? So it's like crest to crest. Now, if your object is moving, it's still going to produce a circle around it, right? But those circles are going to start getting closer and closer to each other in the direction of the movement, but further and further away in the direction opposite to the movement. If you are standing on the side, you see zero change. There's no change in these wavelengths. All right. Increasing velocity. So as you go faster, you see that there is a higher change. The faster you go, the smaller these wavelengths get. And because we can measure that, it can help us figure out the velocity of stars and galaxies. So we call it, when it is getting closer to each other, when things start getting closer to each other, is a blue shift, and when they get further away from each other, it's a red shift. And we have our beautiful Doppler formula. So we have Arcturus. We know that at some point the Earth is moving away from Arcturus, and at some point the Earth is moving towards Arcturus. And we want to know if Arcturus is moving towards us or away from us, so we do some math. We look at the spectrums, we say this is our original wavelength, our lambda naught. Here's the change in our wavelength, our delta lambda. C is the speed of light, it's given to us, and that helps us find the velocity. So, very important to remember that the things you can measure from the Doppler shift, particularly for this lab, is 1, the orbital velocity of Earth, 2, the radial velocity of Arcturus, and 3, the radius of the Earth's orbit. You found all 3 of those things using the Doppler shift, okay? Now is the HR diagram. The brightness, apparent brightness of stars. Apparent brightness depends on how far away it is from Earth. So your stellar luminosity tells you how much light energy is emitted per second, and that changes based on how close it is to Earth, on how bright it looks, right? So that's why it's apparent. Absolute magnitude is taken from 10 parsecs away so that you can compare all your stars. Your stellar luminosity is dependent on surface area and temperature. Those are the only 2 things that can change how much energy is actually output from each star. But how it looks, how much is output, changes based on where it is compared to us, to the distance from Earth. Our apparent magnitude is little mv, and our absolute magnitude is big mv. The V stands for visual spectrum, of course. Absolute magnitude is 10 parsecs away. Alright. Spectral classification, don't forget the Oh, be a fine girl, kiss me. Alright, that's how we can remember what our spectral types are. O stars are the hottest, they are blue. M stars are the coolest and are red. And M stars tend to have more lines in their spectrums because they are cool enough to make elements. They're not just constantly tearing the elements apart. Alright, so here's our HR diagram. We know how hot our sun is, we know how bright our sun is, so we plot our sun. And then we plot a bunch of other stars. And now we have our main sequence. Beautiful. They all fall into this wonderful pattern. And this main sequence is very helpful to us. Now, this is a really important part. I think it's really cool and fun, so please try and answer along with me as we go. You can see a really cool picture of the main sequence with a bunch of stars on it, but these stars over here are a little older, they're getting a little bigger. These stars are also bigger. These stars are smaller. They're white dwarfs. Remember, every star on the main sequence is a dwarf star. So from there you have your subgiants, your bright giants, and your supergiants. Supergiant A and supergiant B. Right? So do learn these, remember them. Don't forget the order of them because it can be kind of important. And again, our sun is a G25, so it's a dwarf star. So here's a little chart. I'll go through these real quick. We have the star names, little MV meaning apparent magnitude, so how it looks from Earth, big MV meaning absolute magnitude. Now when you have both apparent and absolute magnitude, you can immediately find your distance modulus. You don't really have to for this, but distance modulus is a pretty neat thing. It tells you how far away a star is from you. You can use it for a lot of cool things. Next we have spectral type. So this is your "Oh be a fine girl, kiss me" scale, right? Or only boys accepting feminism get kissed meaningfully, or whatever other silly mnemonic device you want to use. But this tells you how hot your star is and your luminosity class, right? So 5s are dwarves. We have a 1 there, that's a supergiant. We have a 3 here, that's a giant, and a 2, which is a bright giant. So our first question is, which star appears faintest in our sky? Where do we have to look to know how things look in our sky? Apparent magnitude. So we come over to our apparent magnitude, and are we looking for a star that has a really high apparent magnitude or a really low apparent magnitude? Well, we're looking for faintest, so we want it to be the largest number, right? So which of these has the largest number? I see 1.4 for Regulus, and Regulus is the answer. Perfect. Which star has the greatest luminosity? Well, where do we look for greatest luminosity? How bright is it overall when you compare it to other stars? We're going to look at apparent magnitude. Absolute magnitude, not apparent magnitude. Absolute magnitude. So you come down here, and now we're looking for greatest, so we want to find the most negative number. I think that's going to be Antares, negative 4.5. So here's Antares. Antares is my favorite star. Which star has the highest surface temperature? So what is temperature? How do we find that? We're going to look at spectral type. That's how we figure out our temperature. Now I don't see any O stars. Do I see any B stars? Yeah, I see 2 B stars here, a B1 and a B7. So which one is going to be hotter? The B1, because B1 is hotter than B7. The numbers go numerically. 1 is hotter than 9, and that sort of thing. So our B1 star is Spica. Moving on, we have which star is a red giant. So this kind of has 2 parts. We know that red means that it can't be, an O star, can't be a B star or an A star. Those stars are, blue and white. They're not red. So that gives us a little clue. But the main clue is giant. Where do we want to look for that? Luminosity class. So most of these are dwarves. We can get rid of them. We have a bright giant, a supergiant, and a giant. Now this is the only one that is an actual just straight up giant, and to verify that it is red, we see here it's a K type, which is a red star. So Aldebaran is the answer. Now we have which main sequence star has the longest lifetime. This one also has a couple different parts to it. First off is main sequence. All stars in the main sequence are dwarves, so we know we're looking at only the luminosity class of 5. That helps us narrow down our choices. Now, has the longest lifetime, the cooler a star is, the longer it lives. So we want to find the coolest dwarf star. These are A's and B's, they seem pretty hot, and here we have a G. Alpha Centauri A. So that is our answer. Hopefully you see how to use this chart, what each of those columns is good for. You can practice, you can write your own questions and practice with these charts. It's really, really helpful to make sure you just really know your information. Stellar parallax. So there's not too much that I'm going to say because most of what you did is in your work, but you have two eyes, and because of that you can see depth, right? If you only had one eye, you wouldn't be able to tell how far away things were, and that's because we use things like parallax to help us figure out where things are. Helps with our depth perception. That's basically exactly what we're doing with our stars, right? If there's a star and it's close enough to us that we can measure parallax, then we can figure out how far away it is. And once we know how far away that star is, if we know that it's 1 parsec away, and we see that its parallax angle, which remember is only half of that measured angle, so only this half, not the whole thing. If we know that it's 1 arcsecond large, if we go to this next star and it's half of an arcsecond for the parallax angle, then you know that it is twice as far away. And since you found out that star 1 is at 1 parsec away, star 2, being twice as far, would have to be at 2 parsecs. Remember, 1 parsec is 3.26 light years. And to find the distance, you say 1 over your p in arcseconds, your parallax. Alright, the Pleiades. We have a star cluster and we graph them, and it helps us figure out some really cool things. So remember that stars in a cluster, there are some things that are similar, some really nice assumptions we make. The first one being distance. Stars in a cluster are all about the same distance away from us. The next being age, because they were formed at the same time, they're all going to be the same age. And also chemical composition, they're formed from the same materials, so they're going to have the same chemical composition, but we don't really use that in this class. But stars in a cluster can be whatever size and whatever temperature they want to be. So that does not change no matter, just because it's in a cluster, alright? Stars can be whatever size or temperature that they happen to be. So here we have a star cluster, and it's some distance away from Earth. It happens to be 10 parsecs. Why is that important? Because it lets us find its absolute magnitude. So here we have our HR diagram with absolute magnitude. We see our main sequence. It's beautiful. Mwah. Now we want to find our apparent magnitude. It's no longer an HR diagram because it's apparent magnitude, right? It's a color magnitude diagram. It is at 10 parsecs, so it happens to be the same as our absolute magnitude, which is very helpful. Now we have a star cluster that's further away than 10 parsecs. So we're going to see that as brighter or fainter. We're going to see it as fainter because it's further away. So on our color magnitude diagram, they are not as bright. Remember, the brightness gets increasingly larger as you go up the scale. So we put it below our original cluster. Next, we have a star cluster that's closer than 10 parsecs. So that one's going to be brighter and therefore higher on the color magnitude diagram. We can sort of compare these. You can clearly tell that if this cluster of stars is the same types of stars, that this one is going to be brighter and therefore it's closer to us. Really good information to find there. If you subtract the apparent magnitude from the absolute magnitude, it's little m minus big M. Alright? And so this one right here, the reason we're using it is because it is the same as your absolute magnitude up here. So that it can be used as your absolute magnitude. You subtract those and you get your distance modulus. And remember, if your distance modulus is, here's a beautiful chart. If your distance modulus is positive, then it is greater than 10 parsecs away. If your distance modulus is negative, then the cluster is less than 10 parsecs away. Right? Good rule of thumb to know. So this is a very important slide. Please pay attention. Right? Very important. Hint, hint, nudge, nudge. Okay. We have two clusters. Cluster A and cluster B. and we know how far away cluster A is. It tells us it's 50 light years. We also know that cluster B is 4 times fainter than cluster A. We can use our inverse square law of brightness to figure out how far away cluster B is, right? So what's the distance to cluster B? Well, you use your inverse square law. You say it's 4 times fainter, so what's the square root of 4? 2. Therefore, it has to be 2 times further away, right? If it's fainter, it has to be further away. So what is 2 times the distance from cluster A, which is 50 light years? 100 light years. You just found how far away cluster B is by using information from cluster A. So, so important. Please, please, please remember this. Ages and distances to clusters. We're almost there, folk. All right. Interstellar dust and gas does 2 things. It gives us interstellar reddening, meaning that we see the stars looking cooler because the light coming from those stars looks redder, and redder means cooler. Why does it look all redder? Because the gas and dust is scattering blue light. Now, if it's scattering light, that means that the light you're going to see is not going to be as intense as it would have originally, so it's going to look fainter as well. And if a star looks fainter, we think that it is further away. That's how we can use the inverse square law of light. So interstellar dust causes these 2 very important things to remember. It reddens the light and it dims the light, making stars appear cooler and further away. All right, so here's Pleiades. We have our standard main sequence, and we can find the main sequence turnoff point here. Once we find the main sequence turnoff point, we figure out what the age of those stars are, and that is how old our cluster is. So age of a cluster is determined by the lifetime of the stars at the main sequence turnoff point. All right? Remember, stars in a cluster are all the same age, so that's why this works. Hubble's lab. We figured out that the universe is expanding because as things get further away, they are moving faster away from us. And it's not just that we're the center of the universe, though we could be. You never know. It's not proven to be anywhere. But at an aliens galaxy, we're also moving away from them. So we are all moving away from each other. You can think of that raisin bread example. You have the dough with the raisins in it. As the bread expands, the raisins move apart, but they still stay in the same place of bread, right? So it's the same thing here. The universe is expanding, just like the bread. So we used our Hubble's law. We had to find our Hubble's constant, which is just the slope of this line. You can either find it graphically by saying, hey, here's the recessional velocity. I'm going to graph it over and find the distance, or plug it into a calculator. If you know one and you know your Hubble's constant, you can find the other. The way we figured this out, we use the images to find distance. Remember that good old inverse square law of light that we keep using? The further something is away from us, the fainter it looks. And the recessional velocity in the spectrums using Doppler shift. As I said, we love Doppler shift. So we plot all of our data, we come up with our line of best fit, we take the slope of the line of best fit, that gives us our Hubble's constant, rise over run, don't forget. And then you just did the rest of the work. You found the age of the universe by saying 1 over your Hubble's constant. That gave you the age of the universe. Rotation of Saturn. Finally, we're on to today's lab. Woo! Took a lot of work, I know. We're here now, and we're going to be using our favorite concept, the Doppler effect. So here's our Doppler effect. Just, again, remember, as the as the source moves towards us, we see a blue shift. As the source moves away from us, we see a red shift. Okay? And we call blue shifts negative and red shifts positive. So you've seen this slide a lot. I'm going to go through it kind of quickly. You have Earth and a star. If they're not moving towards or away from each other, they could be moving side to side. We wouldn't know. We only know that they're not moving towards or away from each other. Their spectrum is going to match up with our lab spectrum. Those absorption lines there match up perfectly. Now, if you have two objects moving towards each other, it's a negative shift because it's a blue shift. It's moving towards each other. The spectral lines are going to be shifted to the blue side of the spectrum, hence the name blue shift. We're just unimaginative people. And if they are moving away from each other, it is a positive change, and you get a red shift. So here we see our lambda naught line, our original wavelength, and the change from where that original wavelength is to where you measure it is your delta lambda, your change in the wavelength, right? This is really important because today we're looking at Saturn, all right? Here's our normal Doppler equation, but we actually have to change it for this one. You can actually write on your Saturn handout. I don't care because you guys, you're pros, and it's at home, so it's not mine anymore. All right, so we have Saturn, and someone took a picture of Saturn and they took a spectrum of it, all right? This little bar here, this is all they took a spectrum of, the entire thing. But you may notice that you see the rings as well as the planet. We don't care about the speed of the rings. We only care about the speed of the planet. So when you're doing your measurements, do not use the very top spectrum or the very bottom spectrum because those are the rings. Only use the middle spectrum. And it's going to be a little more complicated now because remember I said everything in the universe, not everything, I take that back. A lot of things in our solar system like to turn counterclockwise. So Saturn's the same. So this side over here is moving away from us. So what type of shift does that have? A red shift. Because that point right there is moving directly away from us. This point over here is moving directly towards us, so it has a blue shift. And in the middle, there is no shift because it's moving directly to the side. Right? So when you're looking at your spectrum, you're going to be looking at lines. You're going to be looking at the top and bottom of the middle spectrum. Remember, there's a top spectrum and a bottom spectrum for the rings, but of the middle spectrum, you're going to be also looking at the top and the bottom. It's a little confusing, I know, but bear with me. So, you're going to have slanted lines. It's okay. It's exactly what we're going to be measuring. But this was our original Doppler equation, and we have to modify it a bit. Because Saturn doesn't produce its own light. It takes the sun's light and reflects it. So that light is getting reflected back to us. It takes a little bit of a longer path, so we have to adjust our equation for it. There's some math for you. Basically, you end up dividing by 4 as well, all right? So you take a quarter of your Doppler effect, and that will be the velocity. Please don't forget that we modified our equation. Now, if you notice here, we have some example spectrums. This is exaggerated. It's not going to be that tilted, but it's exaggerated just to help you out. See what we're doing here. The very middle is the original lambda naught wavelength. The top shows you a red shift, and the bottom shows you a blue shift. So you're going to be measuring the changes in that wavelength. But this would be really hard trying to find the middle every time, right? So instead, we use reference lines. Here is a reference line. Always keep your reference line to the left of the spectral line you're looking at. You can choose whatever reference line you want. If you want to use reference line A for all of them, be my guest. But you must keep your reference line to the left of your spectral lines. Here are your spectral lines, right? You can't use these ones because they're not to the reference line is not to the left of them, right? So you can only look at this line now. We measure from our reference line to the top of this spectral line. It doesn't matter what spectral line you choose, just make sure that you measure the top and bottom of the same spectral line. Don't switch spectral lines as you're doing this. All right, so you can use any reference line, you use any spectral line. It doesn't matter because all we're looking for is the change. Right? So you measure from here to here, then you measure from here to here. You write those numbers down in your graph. Remember, this is top and bottom of the middle spectrum. I cannot emphasize that enough. So, the top minus the bottom would be the change in your lambda, right? In millimeters. Make sure you measure in millimeters. We have our other information. Here's something new. Your lambda naught is, in this case, 6,200 angstroms. Angstroms are, it's symbolized with that A with a little halo on top. Angstroms is times 10 to the negative 10. Nanometers would be times 10 to the negative 9. So this would be 620 nanometers. But angstroms, it's a little bit of an older unit, and this lab was just written in them, so we have to work with it, all right? Don't be scared. It's just like nanometers, but 1 decimal place over, 1/10 place over. So finding the rotational period of Saturn. The period, it's time, right? Time equals distance over velocity. The distance is going, it's just going in a circle, right? So it's the circumference, 2 pi r, and the velocity, right? So to find how fast it's going, you just found the velocity. So you're going to plug in 2 pi r over your velocity, and you get how fast it's going, how long it takes for 1 rotation. And that is the end. If you have any questions, please do not be afraid to ask. If you have any questions over any of the labs, remember your final is coming up. It is next week. Do not be late. Do not miss out. If you have questions, comments, concerns, please email me. I will be glad to help you. All right. Have a wonderful day.